Oh, John can't hear either. Okay, sorry. Oh, you can hear now, John? All right. Brandon, can you hear? Okay, good. Sorry about that. I don't know what happened there. Maybe we had an internet problem. All right. So back to our screen here. All right. So we want to convert this now to a logical schema. We can start in a variety of places, but who can tell me what one of the elements of our logical schema is going to be? Remember, the logical schema will tell us all of the, relations that are part of our database. So what's one of the relations that would be part of this database? How about karate student? That would be one of the relations. Each one of these boxes is one of the relations in our database. So to begin converting this, we would have to essentially start with one of these boxes as one of the relations. So we can start with karate student. What would be the attributes of that relation? Yeah, the karate ID, the enrollment date, those things would be the attribute. What do we do about name, address, and account? What do we do about those composite attributes? Sorry? Well, we indent them in the ER diagram, but how do we represent them in our database? Our logical schema is going to tell what fields we're going to need in our table. How do we represent those composite attributes? Well, we're going to need a field for each of the lowest level composite attributes because we want to be able to track that. So our karate student relation is going to have karate ID. It's going to have enrollment date. It's going to have a last, first, and middle name. It's going to have a street, city, state, zip. It's going to have a card number, an expiration date, a CWV, month, day, and year for date of birth, and a height and a weight. Okay. So those things are certainly going to be attributes in our schema. All right. Now, who remembers when we were talking about one-to-many relations early on in the class? Is the referenced relation the one, or is the referenced relation the many? Anybody remember? We talked about a referenced and referencing relation in our discussion. The referenced is the one. That's exactly right. So in this case, we have this relation. We have registration. And we have many karate students are registered with the same school. So karate student is the referencing relation. It references school, right? Remember we had that, we talked about the direction of the arrow and all that good stuff. So another attribute that we're going to need in karate student is something that allows us to reference school. So we need a foreign key in karate student to reference the school ID. Does anybody have any questions on that? Does that make sense? So we would need to look at all of these things that karate student references. And actually, we only have one, many-to-one relation from karate students, and that's school. All the other relations are either one to many or many to many. So the only foreign key that we would need in karate student would be a reference to school, because it's many to one. Okay. Karate student is only the referencing relation in one of these relations. For the others, it's either the referenced or it's a many to many. Make sense? So the first thing you do when you're building the logical scheme of karate students is look for where it is the referencing relation, because you're going to need a foreign key for that relation. Okay. So let's look at that. So here's karate student. So, sure enough, we have the karate ID, we have the enrollment date, last, first, middle for the name, street, city, state, zip, card number, expires, CWV, date of birth month, date of birth day, date of birth year. And we have that foreign key for school ID because this is a referencing relation for that. Okay. So now let's look at teacher. Every teacher is a karate student. So teacher is a specialization of karate student. When we have a specialization, we need to know what that's a specialization of, right? So we need to be able to reference what's called the generalization of that thing. And the generalization of teacher in this case is a karate student. So what do we need to include in our teacher schema? Yeah, Zach? Well, you wouldn't want to include all the attributes because those are already stored in karate student, but you wouldn't want some way to reference those attributes, right? So you'd need the karate ID, right? All right, so yeah, and that's exactly what we've got here. Title, all teachers have a title. So, we certainly need the title in the teacher relation. And we also have this karateka ID that references karate student as the generalization of that teacher relation. Okay. So, that kind of covers these two portions of the logical schema, but we still have to worry about all these other relations between karate students. We have to take a look at those. Generally we'll find out that, when we get to some of the things that refer to karate student, we'll have those covered. But the ones that we're not going to have covered are the many-to-many relationships, and those are the ones we're going to have to address separately. All right, so let's look at federation. What are the attributes that we need for federation here? Sorry? Everything inside it. Yeah, once again, for the headquarters, though, we have a composite attribute here. So we would need those individual fields of, headquarters, the city, street, city, state, and zip and country. So those would have to be attributes. Do we need any keys, any foreign keys in federation? Is it the referencing relation in any of its relationships? Right? All the arrows point to it. It doesn't have any arrows that point away from it. So it's always the referenced relation. So it doesn't need any foreign keys, right? Does everybody understand that? It's always the referenced relation. It's never the referencing relation. So it never needs any foreign keys. Federation one. Okay, and sure enough, when we look at that, we see federation doesn't need any foreign keys. We'll look at school now. School is referenced by karate student. We already took care of that relationship. Does school have any, does it reference anything? Well, we've got an arrow pointing away from school up to federation, right? So we need federation ID as a foreign key for school. Because school, the school has a federation that it operates in. And we can see that from this picture. So for school, we would include all the attributes for school. We would need the federation ID to implement that belongs relationship. Oops. Okay. So the registration relationship we've implemented by a foreign key in karate student that references the school. And the belongs relationship we've implemented by a foreign key from school that references federation. Okay? So essentially, we would lay out the schemas here. We would lay out all of these schemas. We would include all of the individual fields, that break out the composites. And then we would look at each of these relationships. And for the one that's the referencing member of that relationship, we would have to include a foreign key to the one that's referenced. Any questions on that or any comments on that? Yeah. Yes. How come a karate student doesn't have a... Right, well, the reason, good question. So we've talked about one-to-many relationships and many-to-one relationships. The interesting thing about karate student and event is that's a many-to-many relationship. There's no arrow on either end of that relationship. And that means that a karate student can attend many events, and an event is attended by many karate students. So we need a way to handle that relationship. We can't put a foreign key to event in karate student because that would only point to one event. And we can't put a foreign key in event because that would only point to one karate student. So how do we handle that many-to-many relationship? That's a great question. Well, the way we handle that is we need to create a special element of our logical schema called attends. And that attends would point to a karate student and point to an event. And you'd have multiple records and attends that might point, many might point to many different, many records might point to the same karate student, and many records might point to the same event, but that's how we implement the many-to-many relationship. Exactly. And that's called an associative entity, because that's what we use to implement a many-to-many relationship. It's a means of associating many karate students with many events, and many events with many karate students. Or a karate student with many events and an event with many karate students. Okay? So that's another thing that we have, after we look at the one-to-many relationships, or in the many-to-one relationships, we have to look at the many-to-many relationships. Everybody good with that? Does that make sense? All right. So when I did this ERD, center the relationship diagram, you'll notice that I have these color codes that I put behind it to kind of break it up into bite-sized chunks. I have things related to organization, things related to tournaments, and things related to events. this is not an official part of the ERD. You know, this is having these areas is not an official part of the ERD. But if you organize your ERD this way, you know, you can kind of take it a bite at a time. So what I did here was I had this area called organization. And I did all of the things in the organization area. I found all the relationships that applied in the organization area. And I did that first. Okay. So when I move to the rank area, I see, you know, a student earns many ranks over the course of their time. You know, this is another conclusion you can draw from this diagram, is that students earn many ranks. You know, and a particular rank might be held or earned by many students. You know, a requirement applies to a specific rank. And, you know, we look at this and we see that there's a one-to-one relationship between a requirement being certified, you know, and once again, we talked about certified as a three-way relationship. Okay, that's another good point here. When we have a three-way relationship, you know, we can't put a foreign key in any one of these individual relations to represent that three-way relationship. So once again, three-way relationships need a schema all to themselves so that we can capture the different parties to that three-way relationship. Okay? So certification, you know, certification needs its own relation in the schema because it involves a karateka, you know, so we need to reference the karateka, we need to reference the requirement that they're being certified on, and we need to reference the teacher who's going to certify that requirement. And we also have an attribute for that relation, which is the date that that was certified. Okay? So when we convert that section to a schema, wherever we have a relationship that involves more than two parties, you know, we're going to have to make that an element of our schema as well. Okay. So going back to our rank area, we also have a many-to-many relationship between the rank and the karate student. And it's an earned relation. The relationship is called earned, and it has an attribute to it. So we also need to make that a separate relation in our schema. Okay? So this is the rank area. You know, we have rank that's earned. We have requirements that apply to that rank. So that's a many-to-one relation. The requirement references a rank. So we need rank ID as a foreign key in that requires relation pointing to rank, because rank is the referenced relation and requirement is the referencing relation. Okay. As I said, for certified, you know, we have three other relations involved in that. So we need the IDs, foreign keys pointing to each of those. And it also has this date attribute that we need to include in that relation as well. Okay. And then the earned relationship says that a karateka has a rank that they've earned, and they've earned it on a specific date. So we model that here as well. Does anybody have any questions on the conversion for the rank portion of this diagram? Okay, events. Here we have the events. You know, we have the event. We have specializations of the event. Each event could be a seminar, or it could be a class, or it could be a tournament. So when we do the seminar relation in our schema, what do we need to include? Since it is a specialization, just like teacher was a specialization of karate. Yeah, we need the event ID. We need to reference the event ID because all those things that apply to the event will apply to a seminar. Likewise, class, likewise, tournament. We also have this preside relationship. We have the sponsors relationship. What do we do about the sponsors relationship? How do we represent that? You need, where do you need Federation ID or event ID? Well, remember, sponsors is a many-to-one, and when we have a many-to-one, we have a referencing relation that's event, and the reference relation, which is federation. So remember, since sponsors doesn't have any attributes, and it's only between two things, and one is referencing and the other is referenced, we can put the foreign key in the referencing relation. Okay? So in this case, we need a federation ID as a foreign key in event that identifies the sponsor of that event. Okay? Does that make sense? Any questions on that? What do we do about a teacher presiding over events? It looks like we can have multiple teachers presiding over a single event. We can also have multiple events that are presided over by any given teacher. So what do we do about that relationship? For that relationship, we need an associative entity that allows us to implement that many-to-many. So we have yeah, this is a many-to-many. So we would have to have a presides relationship. Yeah, actually, I left it out here. We need to include that. Actually, presides would need to be a separate relationship to implement the many-to-many. Fix that. So we would have presides, and we would have an event ID and a teacher ID. For the presides relationship, since that is many-to-many. Yeah, we need a presides relationship since that is a many-to-many relationship in this model. Okay, here's presides. And we need to include role in that presides relationship because a teacher has a role when they preside over an event. You know, they might be the leader or they might be assisting. Okay, so we need the presides relationship in there. But an event has a sponsor, so we'd have a foreign key that points to the federation that sponsors it. You know, that would institute that relation, that sponsors relation, since that is many-to-one. And we would also need a foreign key to the Zoom info. Because that would identify the Zoom that's associated with that event. Okay? All right. And each of the specializations of event, seminar, class, and tournament would have to reference their associated event ID. Okay, so that's the events section. And then just to wrap it up, we would have the tournament section. You know, once again, we would look for those relationships that are one to, or many to one. And the one would be the reference relation, and that would require a foreign key in the referencing relation. So includes is a many to one relation between bracket and event. You know, so we would need the includes relation there. And likewise, match, you know, match has multiple relation, or has references multiple karate students, one of which is the red and one of which is the blue. So we would need a referencing, you know, that's the referencing relationship, and the reference relationship is karate students. So we would need a foreign key to karate student. And likewise, referee for teacher, and likewise earned awards. I'm sorry, earned award would be an associative entity because match and award is a many to many. Okay. All right. So let's look at the rules explicitly here. You know, I've gone through this example. Let's look at some specific rules here. Let me go back a little bit. Okay, here we go. Okay. So, you know, as I said, we convert these entities, individual entities, to relations in the schema. And each entity and relationship set has a unique schema that is assigned to that entity. And the schema has the columns that correspond to the attributes. Okay. So, you know, those things that are in the box, you know, we need to make sure that we represent those. Okay. Now, a weak entity set, you know, a strong entity set will have an ID, a primary key. A weak entity set would refer to that strong entity set, you know, would need a key to identify its associated strong entity set. So in our example, back to our example, we had a weak entity set here, which was bracket, that's included in tournament. So we would need a tournament ID, you know, or an event ID rather, that would identify that bracket. And we did that in our implementation. Okay, composite attributes, as I said, you need the name of the lowest level attribute. Now, what if you have a multi-level attribute? What if, I mean, a multi-valued attribute? Phone number, we were discussing. When you have a phone number, you know, somebody could have multiple phone numbers. They might have a home phone and a cell phone. The way you deal with multi-valued attributes is those need to be a relation in your schema as well. So we would have phone number, and the phone number would refer to a karate student, let's say, and it would have a type, you know, mobile, home, and then the number. So you would need a separate number for that. So so multi-valued attributes would need their own relation. And you can see that here. Yeah, yeah. Nina. Yeah, I mean, that's exactly what I tried to explain. I didn't do it well. But yeah, that relation would be phone number, and the attributes of that relation would be the ID of the person whose phone number that was, and the phone number, and you could have multiple of those for any given ID. Okay. As I said, when you implement a many-to-many relationship, you need a separate, what's called associative entity or associative relation that implements that many-to-many relationship. And to the extent that the relationship itself has attributes, you would need to include those attributes in the relation. Okay. All right. Yeah, for a one-to-one relationship, if you have a one-to-one relationship, either side of that one-to-one relationship can have the foreign key. So either end of the one-to-one relationship could have the foreign key. Okay. All right, so we've covered generalization and specialization. All right, so how are you guys feeling about this? Does this make sense to you? Do you have any questions on this? If I gave you a, not this upcoming test, but in a future test, if I gave you an ER diagram, do you feel like you could implement the logical schema that goes along with it? Maybe. All right. All right. Well, in your assignment, in your upcoming assignment, you're going to be asked to draw an ER diagram like this for your hobby. And I'm thinking I might add to that assignment, that maybe not graded, but I'm going to ask you also to convert that ER diagram, just for practice, to a logical schema. And that's certainly something that you guys are going to do for your group project, okay? So, please think about what you want to use for your example. And, that homework assignment is due, I guess, it's 2 weeks from now. All right. So let's talk about some common mistakes on the ER diagram. Here we have a student that's a member of a department. And a mistake that sometimes gets made is that the department name will be included in the student, in the student record, rather than just a foreign key to department ID, let's say. So, you generally don't want to repeat information that is contained in a reference relation, in the referencing relation. That's a common mistake that's made in ER diagrams. Okay. Another mistake that's made is you should have a pretty good reason for assigning attributes to a given relationship. You want to make sure that if you assign attributes to a relationship, there's a reason for those attributes to be there and that they don't represent a different entity or different relationship. Like in this case, a student is a member of a section and it's giving an assignment and marks to the student in this section. A better thing might have been to establish a separate entity that was grades, and the student would have a relationship to grades, and the grades would have a relationship to the section. Okay? So rather than applying an assignment and marks to a relation that just tells what students are in what section, it would be better to make a separate entity with a separate relationship. Make sense? Any questions? All right. Okay. So here's the alternative. A student receives grades in an assignment, and an assignment is associated with the section. So, this is the way that mistake would be corrected uh, in the entity relationship diagram. Okay, you often have to decide when something is an entity unto itself versus when it's an attribute. In the case of phone number, for example, a phone number takes on multiple values. You don't want to have a field in your table that, might be one phone number or might be multiple phone numbers. So it probably pays to separate that phone number into an entity set of its own. Okay, so that's another common mistake. And we're going to talk about this when we talk about normalization in our next section. This is part of the normalization process, is you want to make sure in your tables you don't have any attributes that take on multiple values. Okay? Okay, use of entities versus relationship sets. A relationship set, you need to be careful about what you include as entities and what you include as relationship sets. If something is bound to take on a lot of attributes, you might want to consider making it an entity rather than making it a relationship set. So just considerations there. Generally speaking, non-binary relationships should be fairly rare. In many cases, if you have a relationship that includes many, many different entities, chances are you've defined too complex a relationship and you can break it up into multiple relationships instead. So generally speaking, you should avoid non-binary relationships unless there's a really, really good reason for having one. So, we've given an example, where a teacher certifies a requirement for a student. But generally speaking, if you have a non-binary relationship, you have the option of creating an entity and, turning that ternary relationship into binary relationships between your original entities and that additional entity. Okay? So here is how you could convert a non-binary relationship to a more binary form. And, this is something to consider when you do your entity relationship diagrams. Okay, let me skip that. Okay, so just to summarize the symbols that we use, we have the entity set, we have the attributes under the entity set. We underline our primary key. For weak entity sets, we use a dashed line to identify the primary key of the strong entity set to which it corresponds. We identify weak entity sets by the double lines around the relationship. Relationship set is a diamond. And the participation of a weak entity or of an entity in a relationship, total participation by double lines. So if there has to be one of the entity, you generally represent that by a double line. I use the 1: notation versus the 0: notation. But if you have one and only one, you could do that with a double line. Okay, here are our cardinality notations. Many to many, you don't have any arrows on either end of the line. Many to one, the many has no arrow, the one has an arrow. 1 to 1, both have arrows. And you can specify limits by the 1 ... notation that I used in the entity relationship diagram that I showed. Okay, if an entity has multiple roles in a relation, you would label each of those roles. So for example, a course can be a prerequisite or a postrequisite. So if you have course related to course via requisite, you would label one of the lines prerequisite and the other one post-requisite or requisite, okay? So, you would label the role name for such relationships. We also have the notation we were using for generalization or specialization. And, you have the overlapping generalizations and you have the disjoint generalizations, and you can represent those in the different ways that are shown here. Okay. So that's the notation in summary. Does anybody have any questions on that? Yeah, Nina. You would have to use the zero. Actually, what you would do generally, sorry, you don't have to use the zero, because what you would do generally is there needs to be one you could use the double line, and if there doesn't need to be one, you could use the single line. Okay. All right. One more comment. The relationship between data elements is just one portion of a model. If you're doing a model of a system, there are ways to model other aspects of the system. When we talk about SQL, we're talking about a declarative language, right? Not a procedural language. You have procedural languages. And you guys might be familiar with some of the notations that you use to represent procedural languages. If you're trying to draw a picture of a program before you do a program, how do you guys do that? What do you use for that sometimes? Did anybody ever flowchart a program or do a flowchart of a program? Sorry? Okay. Flowcharts are one way of representing a procedural program. In a flowchart, in a flowchart, statement. This is the other direction. I have a loop statement. Have a loop statement. You can have all those things in a flowchart. That's one representation of a procedural language. All right. Unified modeling language provides a bunch of different models like this, like an ER diagram, like a flowchart for modeling systems. And UML has a slightly different notation for the diagrams that it specifies. It specifies class diagrams rather than relational data diagrams. But a lot of the concepts that you can use in UML to represent the objects in an object-oriented system are very similar to the ones that you use for data. Okay, so you'll see in these slides, you'll see the equivalent notation. This is not a UML class, but you'll see that there are many of the same types of notations if you do UML. Okay, so we're not going to get into a lot of the detail of UML, but if you do use UML for modeling a system, there will be a data element of your system design, and the way that data element of your system design is captured, the objects in your system in particular, is via diagrams that look very similar to what we've learned in class these past 2 days. The other thing is in UML, you have other diagrams that help you represent other things, like functional requirements, like data flows, like workflows. So let's look at some of those. I like doing this because, as I said, when I was doing system design, I did a very small bit of database development, actually writing the SQL code and all that. I did a whole lot of system specification. And the language that we used for this specification were diagrams, because before you build a system, you want to make sure that you've got it right. And it's cheaper to change a diagram than it is to change code. So here are some examples of some diagrams that you use beyond the PER diagram model system. So we have object diagrams, and similarly, that will show the relationships between different objects. And you can have object hierarchy diagrams that show inheritance rules between classes and objects for those of you who are object-oriented programmers. So you'll have those diagrams, that will help you communicate to your stakeholders what the relationship is between the different objects in your program. So that's one model. You also have an interaction diagram, also known as a call flow. And this shows messaging interactions between different elements of the system. So if you're building a network-based system, and you have different elements on your network that talk to one another, you can show the messages that flow between those elements with this interaction diagram. So here's an interaction diagram for, a system authentication. So the user types in their login, and that gets sent to a login screen. The login screen issues a request on behalf of that user to the server. The server issues a one-time challenge, a challenge for the user to respond to. The user responds to that challenge. The server validates that response to the client, to the PC, and the PC lets the user log on. So that's an interaction diagram. Okay. Another important diagram is called a use case diagram. I was doing an example of this for one of my classes, one of my a high school summer thing. And I used Uber as an example. If you guys were developing the Uber application, you would have a couple of different people that you were developing it for. Who uses Uber? Passengers use Uber, right? You use Uber to find your ride. So, there's a set of things that Uber does for passengers. Who else uses Uber? The drivers. Yeah, the drivers. The drivers have a different interaction with Uber than the passengers do, right? Drivers, they're told the ride is coming. They get their they establish their bank account into which Uber can deposit their fares. Things like that, right? Who else uses it? Who's the other user of Uber? Sorry? Yeah, exactly. The people in charge. So there are 3 use cases for Uber. Uber has to present one use case for passengers. Uber has to present another use case for the drivers. And Uber has to present a third use case for the people who, understand how well they're doing in assigning drivers and whether those drivers are doing what they're supposed to be doing and all that good stuff, and measuring the success of the company, right? So another thing that you do before you build a system is you identify the use cases for the system. And, you can represent that in terms of a use case diagram. And the last diagram that I want to talk about explicitly today is called the state diagram. Any of you see the movie The Imitation Game? The Imitation Game is about a gentleman named Alan Turing. I don't know if you've ever heard of Alan Turing. Yeah. The Germans had this coding machine called an Enigma machine. And the Enigma machine was thought to be an unbreakable code. It was kind of like a typewriter, a mechanical typewriter, but it had these disks. And the disks would translate whatever character you typed into another character, and they would rotate each time. So each time it would translate into a different character. Even if you type the same character, you'd get a different character. And nobody could decipher it unless they had these disks and knew how they were originally set and all this stuff. And, it was thought to be an unbreakable code. So they got together a team in a place called Bletchley Park, I think, in England. And the team was composed of like all the greatest mathematicians in the Allied forces, in the US and England and all these different places. And it was led by a gentleman named Alan Turing. And Alan Turing invented this idea of a state machine, where things change state based on different events. You have something, an event happens, and it enters a new state. And this notion of a state machine was used ultimately, along with some very good spying and intelligence, to break the Enigma machine. But the invention of the idea of a state machine by Alan Turing is what created programming languages, basically. Okay? So if you talk about the father of computer science, who is the father of computer science? You could make a very good case for Alan Turing as the father of computer science. So that's a bit of a history lesson for you guys. But the reason I go there is because, in addition to some of the things that you're more familiar with, one of the ways that you could represent the system is in terms of its states and the transitions that move you from one state to another. So are you guys gamers? Any of you gamers? Yeah. So games do this, you're playing like, and I'm not a gamer. But if you're playing something like Call of Duty or something like that, or, one of these games where you're traveling through a landscape, you could be walking or doing whatever in travel mode. But if an enemy appears, you suddenly change state and you're in some kind of combat mode. And, during that combat mode, you might be shooting at the enemy, and ultimately you kill the enemy. The enemy is defeated, and then you go back to walking, go back to travel mode. So that's another thing, if you're developing a game or something, for example, where you're moving from the state to state, you might want to show what those states are before you develop the game. And you might want to get feedback on that from, a focus group of potential game players, right? But one of the ways you can model that is through a state diagram. So, when you model a complex system, or you're going to build a complex system, it helps to build these models first and review these models with your audience so that you make changes before you build, so you don't build the wrong thing. So, we've covered ER diagrams. That's just one type of model. That helps define what the data is, makes up your system. But you have these other models as well. Okay? All right. And that is the end. So that's it for today. I'm going to remind you of your assignments. You have there was an assignment due. When was it due? Was it due Tuesday? Remind me. Hang on. Yeah, the intermediate SQL. Okay, so that assignment, if you haven't turned in that assignment, I'm going to be going over that assignment soon. So please, even if it's late, turn it in, please, because I'd like to make sure you get some credit for it. Okay, the next thing that you have to do, the next thing on your to-do list is you've got to get with your team and you've got to select your data set and roles and responsibilities. And that's due November 9th, which is Tuesday. Okay, so please get with your team to work that out. And if you don't get with your team, you might be assigned a role or responsibility that you don't want. So, please make sure you get with your team and work that out. Thursday, we have the test. And then you guys have an assignment that's due shortly thereafter to write your simple JDBC program. And then a week after that, or 5 days after that, your ER model will be due for your hobby. Okay? So that's what we got going. And I'm going to end class there. Any questions, comments, final thoughts? Was this interesting? Was it right? All right. You guys on the recording, I hope, or on the WebEx, I hope you guys got all of this. Was it all right for you guys?